All right, so our last section in chapter 6, let's look at some review briefly. An isosceles triangle always has what? Two congruent sides. Could it have three? It could if it were an equilateral triangle. So all equilateral triangles are isosceles, but not all isosceles are equilateral. So therefore, it always has a minimum of two congruent sides. An equilateral triangle is also called, we just said that, isosceles. Cross out the lengths that cannot be side lengths of an isosceles triangle. That's two. First one's out. What about the second one? Can that be? Yeah, sure it can. What about this one? It's 3, 6, and 3.6, 3.6. And what about this one? Yes. So today we're going to look at a trapezoid. So here's your definition of a trapezoid. A trapezoid is a quadrilateral with exactly one pair of parallel sides. So let's add that to our visual aid over here on the board. So we're going to add, because notice that the definition of a trapezoid says it's a quadrilateral. It does not say it's a parallelogram. It is a quadrilateral with exactly one pair of parallel sides. Exactly. Not at least, exactly. And so on here you can see that these would be the one pair of parallel sides. And so we're going to put an arrow out over here and put trapezoid, because it is not part of the parallelogram family. And its definition a quadrilateral with exactly one pair of parallel sides. And you need to know the parts of a trapezoid. And this is a beautiful display right here of the parts of a trapezoid. The bases are the two sides that are parallel. And then they call the two sides that are not parallel legs. And you have four sets of base angles. These two belong to the lower base, and these two belong to the upper base. So do know that your bases are the ones that are parallel. So if your textbook mentions anything about the bases, immediately your brain is making the connection, oh, those are the parallel sides. If they talk about anything about the legs, oh, those are the two sides that are not parallel. Because you're going to have one set of sides that are parallel and one set that are not, always. And then trapezoids not always look like this. They could look like this. They could look like, they could be standing on end and look like that, where these are the two pairs of parallel sides. So they don't always look like the picture. So number 4, cross out the figure that is not a trapezoid, and you have to go based upon what you think, because there's no markings in there. So you're looking for only one set of parallel sides. Does this match that? Yes. How about this? Yeah, it looks like these sides are the ones that are parallel. How about this? A hexagon cannot be a quadrilateral, right? It doesn't meet that base definition. What about this? Looks like this one, right? So that is. Circle the figures that can be divided into 2 trapezoids. Then divide each figure that you circled into 2 trapezoids. So see if you can convert those into trapezoids. And I want you to talk to a friend about this one, because this one can be hard. It's hard, yes? How many out of these figures, how many of them were you able to split into two trapezoids? 1, 2, Dominic, which 2? The second one and the fourth one. How'd you split the second one? This way? How? That way? This way? Come show me. Okay? Put that on there. Oh, we'll put it on. Okay. So now that he's done that, right, would you agree that those are two trapezoids? Hard to see, right? Thank you. The one that was easy was this one, true? So, because you already have these sides that are parallel, and it doesn't matter where you put that transversal, if you will, so long as it's not a diagonal. And then this one, you could have put from any two vertices, right? I'm just going to put it through here. But you could have done it from any of your vertices. If I did it here, you'd have two. It doesn't matter because it happens to be a regular hexagon. So that one was the tough one. All right, flip it. We have several theorems related to trapezoids. So today we're going to spend purely on trapezoids. Tomorrow we'll be on kites. So theorem 6.9 says, if a quadrilateral is an isosceles trapezoid. Well, we have to talk about what isosceles means. What do you think it means? What does isosceles triangle mean? Because the reason why they brought that up at the beginning. At least what was congruent? Two sides. So if a quadrilateral is an isosceles trapezoid, then each pair of base angles is congruent. Okay. What you don't know is in an isosceles trapezoid, the legs of an isosceles trapezoid are congruent. So I've got a picture here of an isosceles trapezoid, and you can see the tick marks right here on the legs. The legs are the non-parallel sides. The minute those legs are congruent, immediately you know it's an isosceles trapezoid, and immediately each pair of base angles is congruent. That means that this pair here is congruent, and this pair here is congruent. They are not, however, congruent to each other. They're just congruent. And so we're going to add that as a special trapezoid down here, just like a square is a special parallelogram. Down here we get the isosceles trapezoid. And what makes it different is the legs are congruent. It implies the legs of the trapezoid are congruent, and what that gives us is a characteristic. Each pair of base angles are congruent. And that only occurs in an isosceles trapezoid. It is not true in a regular trapezoid. Only if it's isosceles. So we're not going to fill out this part here. We already did that. We already marked up our picture. But look at question 8. If ABCD is an isosceles trapezoid, then segment AC is congruent to what? There's something else that's interesting that you may not have known. And they're really just, oh, we skipped over it. Theorem 612, if a quadrilateral is an isosceles trapezoid, as we say, they're not telling you, we skipped over it, then the diagonals are congruent. What is that similar to? What other figure are the diagonals congruent to?
Square.
Or the rectangle, right? You want to say the rectangle mostly because the square is a rectangle, but that does not mean, that's the only thing that they have in common. If I said what figure, in what figure are the diagonals congruent, you could say in an isosceles trapezoid or a rectangle. But you have to be careful with that because that doesn't mean that they're one and the same. It doesn't carry any of the other characteristics of a rectangle. So the diagonals are congruent. The diagonals do not bisect each other as the rectangle diagonals do because it's not a parallelogram. So be careful with that little piece of information. So I'm going to star this one because it's often misunderstood. Just be careful. So we've got A to C. I'm going to draw that in here. And here's the other diagonal from B to D. Draw that in there. You can see that they do not bisect each other. So segment AC would be congruent to segment BD. And question 9 says, if ABCD is an isosceles trapezoid and AB is 5 centimeters, what do you know about CD? It should also be 5 centimeters because it's the leg opposite. The side opposite is the other leg. So you're not going to label up your leg, base. And it doesn't matter what the trapezoid sits on. It doesn't have to sit on its base. The bases are always the two parallel sides. Then we have one last theorem that we're going to work with today. It says the trapezoid mid-segment theorem. We've looked at the mid-segments before on the triangle, right? But this one's of a trapezoid. It says if a quadrilateral is a trapezoid, then the mid-segment is parallel to the bases, and the length of the mid-segment is half the sum of the lengths of the bases. So this is similar to the mid-segment of the triangle. The mid-segment of the triangle was half of the base that it was parallel to. So on both the triangle and the trapezoid, the mid-segments are parallel to a base. But in a trapezoid, because the bases are parallel, we've got two bases. So that mid-segment is parallel to both of those. And so because it's parallel to two bases, we have to take the sum of those two bases and divide it by 2. So we're really averaging the two bases, and that becomes your mid-segment length. So as you look over here, this is your mid-segment length. I know it's a mid-segment because the picture tells me that these pieces are equal and these pieces are equal. So M and N are midpoints. And consequently, you've got two different equations we could set up. This is one of them. So Mn is equal to half the sum of RA plus 2P. We could also multiply both sides of this equation and say twice the length of the midsegment is equal to the sum of the bases. So you could use that also. So you could use that twice in the midsegment is equal to base 1 plus base 2. With a fraction. So 2 of these equals this plus that. And the other thing it's saying is that if MN is a midsegment, then it's parallel to both of these. It's parallel to RA, segment RA, and segment 2B. And so then our final problem here says a fan has 15 angles meeting at the center. Those are all your angles. What are the measures of the base angles of the congruent isosceles trapezoids in its second ring? So here's the second ring, right here. And so they've taken out that piece right here. We've got this angle, this angle, this angle, and that angle. So how many isosceles trapezoids are there in each wedge? 2, right? This one and this one. Don't you agree? Because these should be equal and those should be equal. And so that makes one big trapezoid, by the way. And so A right here, this is one big triangle, is equal to 360 degrees plus, is that a plus? That's a divided by, what's that? 360 degrees divided by what? Because this is all angle A here. Aren't there 15 of them? So we divide it by 15, and what do we get? $24. There's 24. We'll finish this with tomorrow's lecture.